Welcome back, everyone. So today we are going to be working on the final example regarding linear subspaces. And by the way, as you might notice, I'm not using the whiteboard, and that's simply because I had a change of location recently. Thus I couldn't bring my whiteboard since it was too large to fit in the car. But yeah, I will be returning to it in about 3 to 4 days. So let's get started. I left just a reminder of the definition of a linear subspace right over here. So for those of you who forgot about it, there's a quick reminder. So let's write down our example here. Final example. This is going to be quite a bit more different than the past examples. Okay, so let's write it down. This is actually also going to be a review of what span is. So the span, let's consider the span of vectors x1, x2, and x3. And we want to ask, is this a valid subspace of Rn? Valid subspace of Rn. Okay, well, we can quickly rewrite this as some constant c1 times x1 plus c2 times x2 plus c3 times x3. Right, and this is just a basic notion of span. Span is all the linear combinations of these three vectors here, or whatever is inside of these brackets here. Okay. So let's look at our first parameter here. Does it contain the zero vector? Well, let's see. So all these C1s make up any number in the reals. We're assuming that C1, C2, and C3 are all members of the reals, right? And 0 is obviously a member of the real since it's just a member of n naught, or the natural numbers containing 0. So we can just set all of the constants equal to 0. So we can write it as equals 0. And that will output the 0 vector. So as we can see, this set of vectors obviously contains the 0 vector. And that makes sense, right? The span of 3 vectors, we've seen in the past, all the linear combinations of that, it will most likely span R3, assuming that you give the correct parameters of that given span vectors. For example, if you just add on to that, if you set each of these equal to some kind of vector, then you might not, since if that set of vectors is linearly dependent, then it might not span R3. However, if it's independent, it will most definitely span R3. Okay. So let's look at our second parameter. Is it closed under addition? Well, we can check that quickly. So we'll set this this linear combination equal to x. Or sorry, we're already using. Yeah, let's not use that. Let's set that equal to, I don't know, y. So that makes up this linear combination here. And let's take another linear combination. let's say that's equal to C4 x1 plus C5 x2 plus C6 x3, x sub 3. And we'll set that equal to z. Okay, so this is completely valid because the span of these three vectors makes up all the linear combinations of those vectors. So we can just pick any arbitrary value of c sub I, right? Okay, so now we can add these two. So we're essentially, this is because they're both a member of the span of x1, x2, and x3. I'm just abbreviating, instead of saying x sub 1, x sub 2, x sub 3, it's just much easier. So all those vectors. So let's find the sum of these two sets. Subsets of, or sets that are a member of this span here. So y plus z. That would be equal to, well, let's think about it here. So essentially we're just adding these like this. And we can see that we have our like terms, we don't have like terms, but we have x1, x2, and x3. So thus we can factor those out respectively with their given coefficients. So we can say c1 plus c4, all of that times x1, plus c2 plus c5 times x2, plus, finally, c3 plus c6 times x3. And now we can see that, well, all of these terms, all of these coefficients of x, we can just assign them to be like some arbitrary value of c. We can say that this is just equal to c7 times x1 plus c8 times x2 plus c9 times x3. They're just some arbitrary scalar constants multiplied by scaling our vectors here, right? And this is obviously a member of our span. So we can just say that this is actually closed under addition, believe it or not. This is a really good thing to understand, and it gives you a lot of intuition behind what span really is. Okay. So now let's move on to, we'll section these off, just like this. Okay. So now our final parameter, is it closed under multiplication? Well, we can easily check this by setting our original, or we'll just say original C1, original span, or linear combination of x1, x2, and x3. So we can just set again, we can just set that equal to y, as we did beforehand. Y equals C1 V1 plus C2. I'm not going to explain this too much, I'm just copying it down from our original. A3. Okay. And now to easily check to see if we can multiply some vector that's a member of Rn, we can easily just multiply that scalar on both sides. So let's just say that some scalar A is a member. Actually, it's not bolded since it's a scalar. Some scalar A. Well, we're saying that this is a member of Rn. Pretty basic. So now that's really our only parameter here. We can just multiply both sides of this equation by a. By a, right? And we get a times y. So we're essentially just taking the scalar multiple of this. So this is equivalent to, or this is basically what we're saying when we're setting. How do I explain this? When we're multiplying a member of the span here by a scalar constant, which is a member of Rn. That's equal to, we're just going to directly move the a, because you know how we're putting a on this side, then we can just transfer the a's to each term here. So we can just say that a times c1 v1 plus a times c2 v2 of this. Finally, plus a times c3 v3. Right? And again, using the same intuitive procedure, we can just say that this is just equal to some arbitrary constant. We can call it, I don't know, maybe, because we've already used so many, I guess we'll just say C10. And then we can rewrite this. We can just rewrite this, we'll just, obviously we already know it's going to go there. Finally, on our last step, we can just rewrite a times y as C10 v1 plus, let's see, sorry, I'm still getting used to this kind of color coding. Oh, whoops. Okay. C11, whoops, so like that, times v2, finally plus, this is quite tricky, C12, v3, finally. Okay, there we go. And now this is obviously, as we've said many times, this equation here is obviously just a member, well, of our span here. It's just three arbitrary constants that are a member of Rn multiplied by our set of, by our span of vectors here. V1, I quickly switched to, I'm very sorry for this. I switched to V instead of X, didn't I? Yeah, I'm really used to saying V, or using V as our vector, obviously, because that's just intuitive. Let me just fix that real quick. So we'll use xi as our notation for this. Just gonna fix this so you guys don't get disoriented. Sorry for that one. Oops. Okay, well, now we have our answer, and we can just happily check mark all of this, because we've just proven all of these via just some basic algebra transformations. So hopefully you enjoyed this video. Hopefully this was a nice wrapping up video on linear subspaces, and we'll continue with linear algebra in our following videos. So have a nice day, and hopefully enjoyed.